Hey everyone, this is Mr. Hausman. We're going to be taking a look at an introduction to magnetism today. We're going to cover a lot of ground, but some of it is material that you probably have some life experience with, whether it was science class or going to the science museum. So you probably have the resource materials that I have uploaded, and we're going to take a look today at some of the first ideas that you may be familiar with. Let's start with magnets in general. Okay, so there's no one who's gotten to high school and hasn't heard of magnets. Maybe you've heard of permanent magnets, horseshoe magnets, electromagnets, maybe the exotic new neodymium high performance magnets. But really, where are they and what do they do? Well, magnets are a naturally found material. In fact, they're everywhere. But sometimes the magnetism cancels out, so it's not always observable. Furthermore, it's used in a lot of electromagnetic switches, as well as a lot of speaker systems and microphones. And quite a few other examples we'll be talking about. So let's begin with magnetic properties. There it is. So magnets have a property called poles. And some people say, oh yeah, that's the ends of the magnets. Well, they can be anywhere on a magnet. Traditionally, they're on the ends, but some of the newest manufacturing companies know how to put north and south, right? Because there's two kinds, a north and south pole, kind of on any two surfaces of a magnetic material. It could be the left and right, the top and the bottom. But traditionally, it's the two ends. Now, magnetic poles exert force, right, on other magnetic materials. They do this by creating a magnetic field. Oh, so we've heard about this before with electricity and static electricity in particular. We heard that charges make an electric field. Well, yeah, there is the ability to create force in a magnetic field. And a brand new unit, and it's ironically one that I guess is popular currently in the news, is the Tesla. No, it's not the car company. It's not even the person, but it is named for Nikola Tesla, whose motors and generators used magnetic fields to generate electricity. So magnetic fields probably also are something you've heard about. So you've maybe seen a picture of a bar magnet like this, or maybe you saw pieces of iron filings forming kind of curved shapes. But let's pay attention to the direction of these magnetic fields. I'm going to switch color. So north poles of magnets generate electric fields that point outward. They go out of the north. And you notice really small detail from the north end of the magnet, there's always arrows pointing away. So pointing away, pointing outward on each of these. The south pole, on the other hand, all of the arrows are pointing inward. And that's not the same as charges, but just like positive charges are the source of electric fields, they go away from positives and they go in toward negatives, there's an analogy here, but they're not the same. So north is the source of magnetic fields that go away, and south, they go into the magnet. Okay? Now, what if the north and south are on the same piece of metal, like this bar magnet? Well, the field lines create loops. They don't always have to. In fact, some kind of go outward and don't loop around. But if there's two poles in close vicinity, they will form these magnetic loops. Magnetic field lines cannot cross. They do the same thing that electric fields do. And when you put two like magnets together, what you notice is that the magnetic fields that are going out of the north and simultaneously into the south created a very strong field between the poles. Well, remember what fields do. Fields are invisible, but they are what cause forces to happen. Gravity fields create the gravity force. Electric fields create the electric force. And now we have a brand new field, the magnetic field. So between opposite poles, you have a strong field and you get an attraction. But then there's what happens when you have two like poles. a north and a north, or a south and a south. Well, what you create is, again, a region where the field lines avoid crossing each other, the field lines bend, or they actually combine, and they create this region of no field in the middle, or zero field. And that zero field is essentially the source of a repulsion. So there is zero to close to zero field between them. And you know the basics, right? North and south attract because of the strong field, and north and south, or likes, repel. Okay, so that's a pretty basic background. Maybe you didn't quite know that the north and north attract because of the fields, or things like that, but that should be background information that you know pretty well. Okay, now let's move on a little bit to some differences between charges. So similarity to charges, there's two types. There's two charges in the world, positive and negative. There's two magnetic poles in the world. They both create fields. A lot of similarities. Here's a major difference. If you try to separate a south from a north, maybe by cutting this bar in half, try to sever it or break it or drop it and snap it, because some metals have some brittleness to them, and they break in half. Well, what happens is the south end that was originally on the bar basically gets a new north end. And so what we refer to magnets is they are dipoles. There's always two of them. Okay, well, some 20th and 21st century physics predicts that there should be some exotic particles, and I am not an expert on these, where something appears called a monopole. And as you'd guess, it's a north without a south, or a south without a north. But they have yet to be confirmed. They've been on Big Bang Show episodes. You can read it in physics literature that they think they're close to identifying them. They were predicted a long time ago, but they have not been identified. That is to say, a single pole by itself. So dipoles are basically means that there are two poles. And I don't want to write always, but let's just write usually. Because in your lifetime, there may be a chance that gets finally confirmed. Okay. So monopoles someday, right? Not that they're going to maybe be created, but maybe that they're going to be identified or discovered, okay? So what do all magnets have in common? A bar magnet, an electron magnet, or things like that. They have, the source of all magnetism is, believe it or not, the movement of charge. Every moving charge, that means proton or electron, creates a magnetic field. Okay, so you pick up a bar magnet or a horseshoe magnet and you go, there's no electrons moving in there. There's no electricity flowing through that piece of metal. And the answer is no, it's not necessarily electricity. Remember, every single electron, let's take the smallest atom, hydrogen, right? And we have a single electron somewhere far outside. And you go, oh, so you mean this charge, this electron, when it, quote unquote, and it never orbits, but when it moves around in the electron shell of an atom, it creates magnetism. And I'm here to tell you to say, yeah, that's part of it. So the part of it is the translation. I don't mean changing it to another language, but translation or movement is one kind of way that the electron moves. Does anyone remember the other way that electrons move? Well, it gets into quantum mechanics. And many of you have been introduced to quantum mechanics through your chemistry class. And there's this property called electron spin. And as it turns out, electron spin in a bar magnet is what really contributes to its magnetism. Okay, now let's go back to an atom that is very commonly, or can be turned into a magnet, and that's iron. Let's go to iron. Iron has electrons around it, many, many electrons. But when you get out to the 4p sublevel, now for some of you that's a long time ago that you had to discuss that. But if someone said, what is the electron configuration for 3D? Trust me on this, go to a periodic table and you'd start at argon. That's the noble gas on the row before iron. And then you'd add 4s2. Then you'd add 3d. Oh, I misspoke earlier. I think I said 4p. 3d sublevel. And as it turns out, iron has 1, 2, 3, 4, 5, 6 electrons. 3d6. But if some of you remember, the way that a d sublevel works is there's room for 5 orbitals. Orbitals are places that are like kind of like the smallest address or the most detailed address for an electron. So it's somewhere in the 3d sublevel, but then to get the 6 electrons, we have to put them in using the exclusion principle, right? That is to say that the electrons want to be separated as far away from each other as they can. So they put 1 electron in each orbital first, and then after that, to become of course, a stable atom, to get the last electron, they have to double up 1 of the orbitals. And what you see here are 4 electrons that are all spinning in the same direction. And this is a weird phenomenon that's been observed over and over again. This is referred to as spin coupling. Now, remember a minute ago we said that electrons that move create magnetic fields? So guess what these 4 electrons do when they all spin the same way? They create a magnetic field that's all pointed in the same way. So you can actually think of each electron as a tiny little magnet. And when there's 4 of these electrons all spinning the same way, all creating the same net magnetic field, they're going to create a magnetic atom. Oh, so I get it. So iron gets turned into a magnet because of its unpaired electrons. Great. But is every piece of iron made a magnet always? No, most iron is not. And that's because of something that gets a little more complicated called domains. I'm going to write it over here. We've got room. So magnetic domains are kind of the next scale up. So if you can imagine a single electron moving around unpaired. Oh, by the way, I didn't mention this. This is a kind of an important idea. Are those electrons, the 2 that are paired up, are they magnetic? Not at all. Those have opposite magnetic fields because they're spinning in opposite direction, and they cancel each other out. So this is uncanceled spin. Now, as I said, let's go the next level higher. What if you put together in a bar of iron, or maybe steel, because that's iron mixed with other metals, and you have about, a billion atoms on one side of the bar. Well, what happens when neighboring atoms have spin alignment is all of the atoms that are nearby start to spin in the same way. That's spin coupling. But eventually, there's other directions, right? Because these atoms and these electrons can be oriented any way possible. Sometimes they're spinning this way. And I'm going to draw these into little regions. And then sometimes the spin is down, pointed in this direction. And then sometimes the spin is pointed maybe this way. Well, if someone said, what's the overall direction of the spin and the magnetic field? Well, this would be an unmagnetized, right, iron bar. Because each of these is totally random in their orientation. Essentially, the magnetism can't figure out which way to go. There's no definitive pole. It's just like a steel bar or maybe an iron nail. And that's great, but then why can you turn that into a magnet? Has anyone ever seen the trick of taking a nail and rubbing it with another strong magnet? One direction. You never rub back and forth. You just rub in one direction. It's kind of like an elementary school or middle school science activity. We could do it at home if we had all the materials. And so you take that nail, and now you use an external magnetic field to kind of spin the electrons, right? So what if I can push all the electrons so that they all point in the same direction? Let's rub the magnet so that all of the domains, So this is a domain right here. It's a region of aligned spin. Here's another domain, a region of aligned spin. But see how, right, they're random. Now what if you're able to get all of the domains to spin in the same direction? And I just arbitrarily made that to the left. Well, what that's going to create is that's going to create a pole on this magnetic piece of iron now. So this is a magnetic bar or a piece of iron. And that's how you make a permanent magnet. The domains are lined up all in the same direction. Now, again, is a domain a single electron? Why are we using the same arrow for spin, which is a property of a single electron, as the direction of the domains? Well, we're kind of like grouping them together. We're saying millions or billions or trillions of atoms in a domain are all spinning in the same way due to spin coupling. So magnetic bars, permanent magnets, are the result of the individual atoms having a magnetic field that is uncanceled and the domains all lined up. That's the leading theory on what makes a permanent magnet. So what other elements can do this besides iron? And the answers are iron, nickel, and cobalt are the three dominant atoms. If you look on the periodic table, they're in the transition block, the D block, and that means they have something in common. They have unpaired D electrons. So most atoms have paired up electrons, and that leads to no magnetism, okay? Now, there are a few other kinds of magnetism. This is called ferromagnetism, and it's due to domain alignment. Ferro, Latin for iron. But of course, a few elements also show this property. Let's keep going. Okay, this page isn't in your packet, so we're going to do this together briefly. So magnetic fields, we've heard about them. Magnetic forces. I've seen that. I've seen a magnet pick up a piece of metal that also has iron in it. Well, a magnetic field has a symbol B. Brand new, magnetic fields. Now, where do they come from? They come from the poles. And the unit for a magnetic field, right, is the Tesla. How strong is the magnetic field? If you're wondering about, like, well, how strong is, like, the Earth's magnetic field? Earth's magnetic field is about 50 times 10 to the negative sixth Teslas, or 50 microteslas. So that's enough to point your compass needle, but it's not very strong, right? We don't see iron objects move because of it, but a needle does because it has very little friction on the tip of a point. So what are these arrows doing here? Well, what we're going to talk about today is how fields and forces interact. Let's actually start down here with something you already know. Let's go to electric fields and forces, okay? And so what creates an electric field? Oh, I remember that. A charge creates... So at the top of the circle is a noun, a charge. It can be positive or it can be negative. It can be a proton, it can be an electron, it can be an ion, but all charges create E fields. Okay? Then the E field exerts forces on other charges. Oh, I remember that when you drop a test charge into an E field, it causes it to accelerate or be pushed away. If it's an inward E field, you drop a test charge in. Let's kind of talk about that. So here's a charged object, and it has an E field that looks like this. Do you remember that from before we were working at home? And now you drop in a test charge, right? And it gets pushed outward. Here's the E field, but for positive charges, the force and the field go the same way. So what we essentially have is we have two phenomenon, a charge creating a field, but then fields exert forces on, let me kind of separate that, on other charges. Well, guess what? There's going to be a connection that we can make over here. So let's go to a color that we can write with. How about a little black? So what if now we say it's a moving charge? Well, remember, because it's charged, it has its E field. But the moment it's moving, it has both. It has an E field and a magnetic field. That's why we call it electromagnetism. But moving charges create what around them? Oh, they create magnetic fields. Those are B's, right? B fields. This was E fields. Well, what do magnetic fields push and pull on? They exert forces, or force, the magnetic force, on. And so basically you're asking yourself, what can a magnetic field push or pull on? It can only push or pull on other materials that have moving charges. So moving charges make magnetic fields, and then magnetic fields can interact, push on, pull on, other moving charges. So the moment the charge is at rest, not moving, static electricity, there's no magnetic properties. That's why we studied static electricity first. But then as soon as we got into electricity, we didn't talk electromagnetism right away, but they are more closely related. Okay, so that's a huge conceptual framework that may help you make a connection. It may take a minute or even a little more than that to really digest that slide. Okay, let's jump into this one. And oops, I was doing something with another class. Let's clean this up. So let's move now to page number 2, in your packet. And let me kind of move things around a little bit. This is the whole page. There we go. Now, this is a pretty challenging idea. Let's talk about its name first. So we're going to talk about this magnetic force on moving charges. Kind of a perfect segue. It's called the Lorentz force law. Lorentz force law says that the magnetic force is equal to the cross product of two vectors. Remember the arrow, the arrow that on top of a letter? Well, what's the first vector? Well, the first vector is QV. I know what Q stands for. Oops, Q is equal to the charge. It's the amount of charge, and that's in coulombs. Let's try that again, in coulombs. And then V is the velocity. How fast are they moving? Remember, they have to be moving, and that's going to be in meters per second. Well, when you cross it with a B field, remember B field is a brand new symbol for the magnetic field, mag field, and its symbol is the Tesla, you end up getting newtons of force. Tesla is actually not a pure unit, it's a derived unit, and we could go into that if you're interested. So let's talk about what a cross product is. A cross product is a really unique mathematical operation. It's a vector operation. And you're like, oh, we did vectors all fall. We added them. That's all we did. We added a vector of velocity to this vector of velocity. We would take this displacement and connect it to this displacement. And we notice how I'm using my hands. We do it head to tail. And the resultant is a sum of vectors. Well, a cross product is a little different. It is an idea that stems from vector math. And when you cross these two vectors, so from a plain simple term, let's talk about crossing as if one vector, right, is going through another vector. It looks like the multiplication sign, but it's not. It's crossing it. So when these two vectors cross, you get a third vector, right? Here's the two vectors that are crossing, and here's the answer, a force vector. Now, when you cross vectors, you have to add in cross product. You have to know the angle between the velocity and the magnetic field. So if they cross at 90 degrees, sine of 90 is 1. If they cross at 45, oh, I forget that one off the top of my head, but it's less than 1. I'm sure you could look it up, and half of you know it off the top of your head. So you have to know the angle between them. So apparently, the angle determines how strong the force is. So a sine of 90 equals 1. So it will be the largest force possible. So you get the largest force on a moving charge that hits a magnetic field if they are perpendicular to each other. Well, some of you know that sine of 0 degrees, well, what kind of cross is 0 degrees? Oh, that means they're moving the same direction. So if you have a moving charge parallel to a magnetic field, or anti-parallel, that's 180 degrees, you get a value of 0. And so that means going parallel gives you no force at all. So that's an important thing to understand. So when you cross two vectors, you get a force. But what's the only kind of cross that gets you no force? Well, when you don't cross, when you run parallel or anti-parallel or parallel, 180 degrees or 0 degrees, okay? So I bet everyone could plug into this formula. Q, charge, times velocity, times the B field in Teslas, given some data, and don't forget, you have to take sine of the angle between them, and that'll give you the force. Well, we're going to do that math, and it's pretty straightforward. It's called the Lorentz force law. It's the force on a moving charge. Here's the fun part. Here's the challenge. The challenge is, what direction does the force go? Well, when we added these two vectors, added them in the fall, like a velocity of a projectile, the hypotenuse was, of course, in the same plane, right? It was XY problems. We used to call them 2D motion or 2D projectiles. Vectors that get crossed immediately involve a third dimension. Okay, so see the person's hand? The person's hand here is got their fingers in this configuration. It's like a little kid who doesn't have a Nerf gun and they want to hold up their hands and play, army or cops and robbers. And so there's your gun. Your thumb is pointed up. Some people have different ligaments, so their thumb goes too far back or too small down. But try to make that 90 degrees, okay? So if I hold it like this, it's 90, 90, no matter what. Now, your middle finger has to go 90 degrees to your pointer finger. So it's like a weird three-dimensional L. I'm going to rotate this around a little bit, and I know that's weird, but that's the shape that every math and physics student learns for cross products. You may actually even do that in math class someday. In math, they may be less interested in the direction of the force and more interested in how big is the force or the vector cross. But in this case, we want to know which way they're being pushed, okay? So rule number 1, don't use your left hand. It's called the right hand rule, okay? So never, ever use your left. I'm going to tell you a time that you're going to use your left later, but don't use your left. Use your right hand. Okay, so your fingers. Okay, so when you line up a problem, you're going to use your fingers or the tip of your pointer finger for the direction of the moving charge. Okay, so we're going to be doing problems on paper. So you line up your pointer finger with the direction of the velocity, the arrow that shows which way the charges are moving. Your middle finger is going to be your magnet finger. Okay? So that finger stands out to the side. So you sometimes have to rotate your wrist. And this is so hard to do on a document camera, so that I have another camera that I'm going to do a short video with where you can actually see my hand on the camera. Okay, so remember how I said it was a 3D problem? Well, what are the 6 directions you can have in 3 dimensions? Right and left. Okay, that's 1 dimension. When you add that to up and down, that's a 2nd dimension. But then to add the 3rd dimension, you have to have a way of showing, right, that it's going out of the page or into the page. So here's out and here's in. Well, I remember this X is like a pirate. Pirate maps use an X, a circle with an X around it sometimes, to show this is where you should dig in to find the buried treasure. Oh, so I get it. So if I'm looking at a piece of paper, a paper problem, or any kind of problem where I can line up one of my vectors. By the way, these are just the directions of vectors, any of the vectors. And one of my vectors is pointing into the page. I can say, oh, you mean circle X, or just an X. Circle dot, think of that as like the peak of a mountain. That's coming out of the page. It would be coming up at you. Okay. Now, we're going to be doing this live in class, but I said I'd record a video. How do you solve this page? How do you find the direction of the force? Not how big is it, but just what is its direction? Okay, step number 1. Turn your page. Watch this. Oops. Turn the whole page. That's going to be a super weird graphic, but I think this is going to make sense. Then what you do is you line up your pointer finger in the direction of the moving charge v. That's its velocity. Then you look on the paper and you go, oh, my magnet finger, my middle finger, my B field, is already lined up. So my thumb is currently pointing straight up toward my face, right? Or toward the ceiling. So I would say, and I'm going to turn the page back. Think I can do that. It's going to be a little weird here. There we go. I can say that my force was, pen, I can say that it was circle dot. So my force is equal to circle dot. You don't have to write a number. You're just writing a direction. Okay, number 2, do you see how the pointer, the positive charge, that's the pointer finger, that's the velocity director, is already going up. So I'm going to keep my finger pointed that way. I know I'm pointing at an iPad that's off camera. But then I notice that my magnet is going into the page. So I have to twist my wrist so that my magnet finger is pointing downward. My positive finger, see how it didn't change direction? It's still pointing toward the top of the page. But now I turn my magnet down, and my thumb is pointing to my left. I hope that doesn't get reversed on the camera. So my force would be a left arrow. That's my answer. Okay? These become a little bit of a puzzle, and it is one of the hardest things that I've ever thought about teaching in a virtual or online classroom. There's videos of this. We'll see if others can show it better. I welcome you to find other videos. Okay, how about number 3? Number 3, I think we're going to have to rotate the page again. Oops. There we go. Okay, now I know the graphics don't line up at the moment. But now, why did I do that? Well, because now my pointer finger, you always do charge first, the velocity and the charge first. But now, which way is my magnetic field pointing? Oh, it says B dot, circle dot. So my magnet finger, which naturally, when I hold out my right hand, this is my right hand, it naturally points toward the middle of my body. But now I have to do a gentle twist so that my magnet finger is now pointing toward the ceiling. And my thumb is pointing to my right. But remember, on the paper, that actually means toward the top of the page. So let me see if I can't get this to go where I want it to go. There we go. Okay, we're back together. Here's where we should be. I believe I found that my force, and please correct me if I'm wrong, it's very hard to do this in a video lesson, is toward the top of the page. So charge, magnetic field, there we go, and it's toward the top of the box. Your assignment is to try 8 of these. You're going to be doing this weird right-hand thing, the physics gang sign, right? The right-hand rule for Lorenz's law. And the only thing I want to warn you about is after number 3, the first 3 are pretty straightforward. 4, 5, 6, 7, 8. They have an electron moving. And you're like, well, it must be the same thing. Nope. Whatever direction you get, whatever direction you get for the force, reverse it 180. So up becomes down. Left becomes right. In, circle X, becomes circle dot. 180 degrees just means the opposite direction, okay? So I will have the answers to 1, 2, 3, 4, 5, 6, 7, 8. They're really just going to be arrows or dots or circles. It seems like an easy assignment, but it definitely takes a minute to get used to. Thanks a lot, guys. Introduction to magnetism. Hopefully